Hello everybody and welcome to Operation Research Lesson 23, Optimization of Integer Programming using Branch and Bound Method. Last time we discussed Lesson 22, Optimization of Nonlinear Programming Problem using Lagrange Multiplier. The objective of this particular lesson is to find the optimum solution for integer programming problem using branch and bound method. First of all, let us see what integer programming problems. A linear program with decision variables restricted to integer values is called a linear integer program. Basically, there are three types of integer linear programming models. The first one is total integer model, that is all the decision variables have integer values. 0, 1 integer model, all the decision variables have the values of 0 or 1. For example, like this. And the mixed integer model, some of the decision variables, but not all, are required to have the integer value. Look, x1 equals 2, x2 equals 3, and x3 equals 1.5. So 1 is not integer. So this is called a mixed integer model. By the way, in practice, mainly the variable of interest have to be integers. For example, if we consider number of laptop, printers, number of human beings, number of refrigerator, number of chairs, number of tables, number of TV, number of mobile, and so on, are integer values. Their values are integer, cannot be fraction. We cannot say 1.5 laptop, or we cannot say 1.7 mobile. But we have to say 1 mobile, 0 mobile, or when I say I have 0 mobile, I don't have any mobile. I can say 1 mobile, 2 mobile, and so on. So in such cases, fractional value doesn't make any sense. So in this case, when we get our decision variables fractional values, we have to rounding off those values to the nearest integers. Rounding off to the nearest integer is a must, just to make sense, right? To make sense. But the problem is when we rounding off those results, we may encounter or we may result in suboptimal or infeasible solution. That is the main problem. If the solution, even the solutions are feasible, the objective function may be not be optimal. For example, look. If we get x1 1.67 and x2 2.9, so if x1 is the number of laptop and x2 is the number of printer, so we have to round this number into the nearest integer, just to make sense, because we cannot have 1.67 laptop and we cannot have 2.9 printer, so we can round off this fractional value to the nearest integer. That is the point. And when we round this fractional value to integers, we may encounter our result may be suboptimal or infeasible solution. That is a problem. So to alleviate such problem or to mitigate such problem while we are solving the integer programming problem, we can use branch and bound method. It is a technique used to solve the integer programming problem. Actually, the branch and bound method is a solution approach that partitions the feasible solution space into smaller subsets of the solution. And a linear programming model solution with no integer restriction is called a relaxed solution. And the optimal solution of the integer linear programming is always between the upper bound of the relaxed solution and the lower bound of the rounded down integer solution. Let us see what's the upper bound and the lower bound with an example. Look, here is the integer restriction or free integer or no integer restriction decision variables. As you see, they are fractional values. So it is a relaxed solution of upper bound. It is upper bound, which is a relaxed solution. And here is the lower bound when we rounded down 1.67, it becomes 1. And when we round it down 2.9 into the lower integer, so it becomes 2. So this value is the lower bound. Here the point is that the optimal solution for the integer linear programming is found between the upper bound of relaxed solution and the lower bound of the integer values. Let's see the examples. Let's see an example for integer linear programming problem with integer restrictions. Look, here is a maximization problem such that here is a constraint and another constraint. So x1 and x2 is greater than or equal to 0 and integers. So this one is the integer restriction, or we can say integer linear programming, because the non-negativity plus that of not only the non-negativity plus the integer values, the x1 and x2, the decision variable should be an integer value. And the other one is a linear programming model solution. A linear programming model solution with no integer restriction is called a relaxed solution. That is the upper bound. So in this case, there is no restrictions of integers for our decision variable. So this linear programming has a relaxed solution, just a regular solution. The decision variable may have a value which is different from an integer value. Their value may have a fractional values. This is the steps that we have to follow while solving the integer linear programming using branch and bound method. Actually, rather than just discussing these steps, it is better to discuss along with the solved example, right? So we have to follow all these steps while we are solving the integer linear programming using branch and bound method. Now let us see along with the solved problem. So this is solved example of linear integer programming. The owner of a machine shop is planning to expand by purchasing the machine's presses and lathes. So the owner has estimated that each press purchased will increase the profit of by 100 and 150 per day respectively. And the owner has a budget of 40,000 for purchasing the machines and 20 square feet of available floor space. The machine purchase price and the space requirements are as follows. Look, this table shows that the press machine requires 50 feet square space, and it requires, or its price is $8,000. And the lathe machine requires a floor space of 30 feet square, and it requires a cost of $4,000. As we know, the number of press machine and lathe machine should be an integer value, right? So this problem is a linear integer problem. And we have to formulate, because before solving this problem, we have to formulate this practical problem into linear programming model. By the way, formulating the linear programming model is discussed in lesson 3, so you can refer it back. How to formulate a practical problem into a linear programming problem. So as to solve using different techniques, the first step is we have to formulate into a linear programming model. So when we formulate this, it becomes like this. Maximization of z equals 100x1 plus 150x2, such that 8,000 x1 plus 4,000 x2 less than or equal to 40,000. 15x1 plus 30 x2 less than or equal to 200 feet square. x1 x2 greater than or equal to 0, that is non-negativity, and integer, because it is an integer linear programming problem, because here we know that in practice, or in reality, the number of press and lathe machines should be an integer. It must be an integer. It cannot be a fraction. Integer value. it is a must to be an integer. So this problem is integer linear programming problem. Now let's start from step one. Step one says that find the optimal solution of the linear programming problem with integer restrictions relaxed. So if integer restrictions are relaxed, the decision variables can have a value of fractions. So first solve the linear program as a regular linear program model without integer restrictions. So we can use either graphical methods that we have discussed earlier. You can refer back to the graphical solution of linear programming problem, or we can use simplex method. Simplex method just to find the solution for this integer restriction relaxed. So using either the graphical method or simplex method, we get this value. We get this value x1 that is 2.22 and x2 5.56, which are not integer. So we cannot say, it is obvious, we cannot say 2.22 press machine and 5.56 laser machine, because those machines can be only interpreted in terms of integer values. The number of press and lathe must be integer values, right? So now the integer restriction relaxed is the upper bound. Here is the upper bound. The values are the upper bound. It is a relaxed solution, and the lower bound is when we round down to 2.22, it becomes 2. When we rounded 5.56, it becomes 5, right? It becomes 5. When we substitute 2 and 5, the Z will be 950. This is the round down integer solution. It is the lower bound, and it might be suboptimal. Anyway, the optimal integer solution for this linear programming problem is found between these two bounds, that is the relaxed or the upper bound and the lower bound, So the solution, the optimal integer solution, will be between these two bounds. Coming to the step 2, select the greatest fractional parts for branching. So now we start branching, but to start branching first, we have to select the greatest fractional part. We have to compare the fractional part. Then create two new constraints for these variables. The result will be, we will see it. Now let's compare 0.22 and 0.56. As you see, 0.56, the fractional part is greater than 0.22. That is, we compare just this fractional part with this fractional part, and 0.56 is greater than start from the largest fractional part just to branch. The farthest from the rounded down integer value, it means. Because x2 must be an integer value, in the optimal solution, the following constraints can be developed. That is, either x2 less than or equal to 5 or x2 greater than or equal to 6. When we make x2 greater than less than or equal to 5, so x2 can be because all the decision variables, don't forget that there is a non-negativity, so x2 can be 0, 1, 2, 3, 4, 5. In the case of what? In the case of x less than or equal to 5. In the case of x greater than or equal to 6, so the value of x2 be starting from 6, 7, 8, 9, 10, 11, 12, and so on, etc. But it cannot be the value between 5 and 6, that is 5.56. Now we convert the value of x2, that's 5.56, into integer value, which is x2 less than 5 and x2 greater than or equal to 6. Now let's form the branch. Here is, by the way, the relaxed, the upper bound solutions, the integer relaxed upper bound solutions. Now we just make a two branch, that is x2 less than or equal to 5 and x2 less than or equal to 6. Now, first, the solution at node 2 is found by solving the following model with the constraint x2 less than or equal to 5. Now let's find the solution. Let's find the solution by adding only one restriction at a time, that is at node 2. So when we found the optimal solution for this model with the integer restrictions relaxed, so it becomes what? It becomes x1 2.5 and x2 5 and z equals 1000. By the way, for integer restriction relaxed, we can use either graphical method because the decision variables are 2, or simplex method to find the solution. So this is the integer restriction relaxed, so it is the upper bound. It is the upper bound. Now we write this here. We write this here. Look, we write here, right? We already write this one, and the lower bound is already known. We just took from this by rounding the fractions into the lower integers. Now the next step is the solution at node 3. Node 3 means here it is. That is, we have to add x2 greater than or equal to 6 into the original linear integer problem. So we add just x2 greater than or equal to 6 as a constraint, and we can use either simplex or graphical method to find the optimal solution for this model with an integer restriction relaxed. So we get x1 1.33 and x2 6, and z becomes 1033.33. So this is the upper bound in node 3, and the lower bound is known, that we take just from the original lower bound. And next, since we do not have an optimal and feasible integer solution yet in either cases, in the case of node 2 x1 is 2.5, that is not feasible, or that cannot be that cannot have any sense, because we cannot have a fractional value of machines. And in the case of node 3, we can also get here 1.33, x1 equals 1.6. That's fractional value, doesn't have any meaning. So since we do not have an optimal and feasible integer solution yet, we must continue to branch the model from either node 2 or node 3. Either node 2 or node 3. Just to choose either node 2 or node 3, always branch from the node with the maximum upper bound. Where is the maximum upper bound? As you see, 1000, let's compare 1033 with that of 1000. So 1000 is greater than 1000 is greater than 1033 is greater than 1000. So let's start from node 3. Variable with greatest fraction is selected. As you see, it is obvious. x1 equals 1.33, where x2 is an integer. So 1.33 is selected. 1.33 is selected with a greatest fractional part. Thus, we have to form two new constraints, which is developed from x1 equals 1.33. That is, x1 is less than 1 and x1 is greater than 2. Now we form the two branches, that is x1 less than or equal to 1 and x1 greater than or equal to 2. Let's continue. Next, the relaxed linear programming model with the new constraints added must be solved at node 4 and 5, here and here. Now let's start just from node 4. So in node 4, we have to add what? We have to add just from this constraint, and we have to add this constraint, because here it is our iteration like this. Now the optimal solution for this model with integer restrictions relaxed becomes relaxed x1 equals 1, x2 equals 6.17, and z equals 1025. So let's write here. Still, we didn't arrive on optimal solution because x2 equals 6.17. Now let's move to node 5. When we iterate at node 5, we have to add x2 greater than or equal to 6, the first constraint is, and x1 greater than or equal to 2. x1 greater than or equal to 2. So in this case, by the way, however, there is no feasible solution for this model. So no solution exists at node 5. No solution exists. So it is just infeasible. We can just check by substitute. For example, if we substitute 6 into x2, 6 times 30 equals 180, and 2 times 15 equals 30. 30 plus 180 is 210. 210 less than or equal to 200 is not feasible, right? 210 is not less than or equal to 200, so it is just infeasible. Now let's return to node 2. Let's now return to node 4. Since there is no comparison between the upper bounds at node 4 and node 5, because in node 5 we get infeasible solution, compare node 2, this node, and node 4. So node 4 has a greatest upper bound. As you see, here it is, the upper bound of node 4 is greater than the upper bound of node 2, that is 1000. 1025.5 is greater than 1000. So let's start from node 4, which is the upper, which is the greater upper bound. So in this case, the largest fractional value is 6.17 because x1 is an integer. So let's have an integer value for x2, that is x2 less than 6 and x2 greater than 7, right? Greater than 7, just to make it integer value. Now let's add x2 less than or equal to 6. Let's find the solution at node 6. When we found the solution at node 6, which is the integer relaxed solution. So in this case, by the way, when we add x2 less than or equal to 6, the other restrictions are this one, and the other restriction is this one, right? This one. So the optimal solution for this relaxed linear program model is x1 equals 1, x2 equals 6, and z equals 1000. Actually, all the decision variables are integer value, and the z is 1000. Anyway, let's continue our iteration up in node 7 just to confirm whether this one is optimal solution or not. Now let's add x2 is greater than or equal to 7 by removing x2 less than or equal to 6. Now it becomes infeasible. However, there is no feasible solution for this model because let's check by the way here. Here when we substitute x2 greater than or equal to 7, actually x2 is greater than or equal to 6, it says, and the other is x2 is greater than or equal to 7. So we can just assure that this is infeasible because there is a conflict between x2 is greater than or equal to 6 means which includes the value of 6 and others, and here x2 includes greater than x2 includes starting from 7. And when we substitute this value, even for example, if we substitute x2 7 into x2 value, that is by itself 210, and x1 is 1, so 15, so 225 is not less than or equal to 200. So we can just prove with this that is infeasible solution. So infeasible, this one is infeasible solution. And now let's okay, we already get the node 2 solution. So now we already find all the solutions. Now the optimal solution become the solution that we have found at node 6. Which satisfies x1 and x2 are the integers, that is the number of machines, that is 1 and 6, and the upper bound is 1000, even the so it is just found between the upper bound and the lower bound, So this is the optimal integer solution. So I have provided you an example just to practice by yourself. This is an integer linear programming problem. So use branch and bound methods to find the solution for this integer linear programming problem using branch and bound method. So the relaxed solution for this problem is this one. Now you can continue using the previous steps. So this is all about the integer linear programming problem solution using branch and bound method. And next time we will meet with another lesson. Till then, have a good time. Bye.